Oh, I think the numbers are slowly stabilizing. So, good afternoon, everyone. Welcome to the now second workshop of Fair Data Principles in Physical Science in NFDI, organized and also supported by Physical Science in NFDI. Few administrative notes in the beginning. This workshop will be recorded, so if you know any of your colleagues who missed it, it will be available on YouTube at a later point. After each of the presentations, we'll have time for discussion. So if you have any questions, you can write them down already during the presentation in the Q&A, or if you use the German version, F&A. And we address them after each of the presentations in the discussion round. If you would like to personally ask your questions after the presentation, feel free to also raise your hand and directly ask ahead. In this workshop, we'd like to present use cases from the consortia in physical science in NFDI, use cases addressing common challenges and maybe also provide common solutions for problems in research data management that we all might face in our consortia. And as you know, research data management does not start with uploading a data somewhere in a repository, but it's really a thing that goes over the whole workflow in research. So today we want to focus on use cases, establishing fair workflows in our research areas. Before we get to the actual use cases, maybe let's start with a short introduction and reminder. What is FAIR about? What are the FAIR data principles? And for that, I would like to give the screen to Dr. Caroline Rehermann from Berlin, the communication and outreach expert from FAIRMAT. Please, Caroline, the screen is yours.
I hope the screen sharing works. And as Michael already said, I will give a very short introduction of the FAIR data principles to get everybody here on board and on the same space. So yeah, what is FAIR? FAIR is an acronym which stands for findable, accessible, interoperable, and reusable. And with this, we mean data is findable when it's possible for others to discover your data. It's accessible if it's possible for human and machines to gain access to your data. It's interoperable when it's possible to combine and exchange data from different sources, and reusable if it's sufficient documented with support to their interpretation and reuse. These are the definitions or guidelines to be fair. But what does this really mean? Because still nowadays, data isn't automatically be fair. And I will guide you now quickly through these four headlines with the analogy of Lego building blocks. As you can see here, it's a chaos, different building blocks. And if this would be your data, it wouldn't be findable in the diverse universe of all of this data. So non-findable data often can't be obtained, or knowledge cannot be obtained from that data. You have the issue that experiments need to be duplicated. You often miss the chance for interdisciplinary discoveries, and searching for data results is often a waste of time and a super high effort. So speaking in this Lego picture, what can we do to make data more findable? So what we can do, just picking out one example here, is we give it a PID. So for example, we don't say, oh, it's a Lego building block. We really give them a specific kind of a product number for what you can see here on the left, this one stud. We will come later to this building block in yellow, and then when it's being in red, you get a different serial number for it. And also not changing colors, but also changing this shape, which you can see a bit more right when you get an additional stud on the side. That this is all clarified, and you have a really unique identifier, which is helping to make your data findable. And just to spread this out a bit more, I won't get into too many details, that you can sort by part, by color, and by category, which is becoming, for example, bricks or plates. And this is one example how you can make your data more findable. So now you made your data findable by giving it a series number, for example. However, now it's, as you can see here in these pictures, it's sorted into these boxes. but they're closed, they are in a shell. You can't really access the data from the outside. And yeah, non-accessible data have the issues that you have issues to use the data to find, and detailed metadata is often missing. You're unable to reproduce or verify data, and there's a lack of clear access. So again, speaking in this Lego picture, what can we do? We need to find a general communication protocol. For example, here we can have kind of a catalog where we can sort for the different bricks and building blocks we have within the Lego system. And then even once we access these, we get more information about the item we are looking at. Speaking in your data, it would be assembled with all of the metadata. For example, which instrument did you use to measure your data, and so on. Interoperability is very often an issue. Since you see these here are all kind of building blocks, they already look different from like the standard Lego one. For example, you have smaller ones, you have bigger ones, different connecting dots, square-shaped connections, round connections. So this is all an issue. And speaking in your data, this means data formats are need to be unified. So it is impossible to compare data that came from different sources if they are like this. The structure of data is different by different researchers, and yeah, there are different labels for data, although researchers are talking about the same quantity. And how can we work on this to improve? So we need to use a formal, accessible, shared, and broadly acceptable language to talk about our data. And just giving you an example again here on this Lego, for example, when we were talking about this topper connection, in literature we found words as called protortion, cylinder, post, stud. We figured out the official word for it, it's stud. So this is going into the topic of ontologies and taxonomy. Again, the same thing. Once you flip your brick, you get this thing, what could be a hollow cylinder, a tunnel, or a tube, and so on. And to be interoperable, we need to agree on one accessible shared language to identify our data. And this goes on, like in this whole universe of Lego, for example, we learned these bigger building blocks are called bricks, and we need to be specific. It's a brick with 8 studs. While this thinner plate, it's a plate with 8 studs. So here you see they have in common 8 studs, but the thickness differs. And here language helps us to really distinguish between those. And to give you some other example of different building blocks, you can have this tile, an arc, a panel, or a slope. So here's an example of this accessible language that we have in this Lego picture. And then, yeah, there's the issue of reusability. Once we now have identified our building blocks, we know them, we have all of it, but what can we do with it? How can I use, for example, this white Lego block again to build something like an ice crystal or a tail from a cat? So talking again in data, an issue is often absence of clear licenses for data reuse, a lack of digitized metadata, inability to define who should create, cited, or contacted about this data, and the inability to assess the suitability of data for the planned reuse. So what can we do to come around this issue? And for this, we need Richard described data or metadata with a plurality of accurate and relevant attributes. So this could mean in this plurality, there should not be any assumption to the user of the data. The author of the data should be as generous as possible with the provided metadata, and metadata should support a variety of possible use cases for the data. So here in this Lego, this means, okay, we have this Lego building block, but what can we do now with it? We can use it in different things. We can build an arc, we can use it to build a cat, it can be the arm of a robot. So speaking in this, data can not only be used in one specific research project, but it can be a support also in other research projects, and yeah, help you there to not only have it this one time used or as a standalone item. And yeah, as a short summary, to be fair, we tried from this chaos or this diversity of data we have to assort it, to define it, to make it accessible, to sort it, to get a unified language that we all use the same vocabulary for the same items we talk about, and with this get generalized construction plans to use this data for multiple research topics. And with this, I just gave you a very, very short summary and with some spotlights from a longer tutorial one of my colleagues gave. If you're interested, you want to learn more about all of these 15, I only picked out 4 guidelines for fair data principles. Feel free to watch the tutorial. You can find it under the left QR. And we also have summarized everything in a comprehensive PDF of slides, which you can also find on Zenodo. And with this, I would like to close my short introduction and hand over to my colleagues with the use cases. And I'm keen to see how you apply these fair data principles to your research.
Thank you, Caroline, for this great introduction. Before we get to the use case, of course, we'd like to also provide you the opportunity to ask questions. I don't see any written down, but if you have questions right now, please feel free to also raise your hand. I didn't see any questions yet. We will also have time to discuss in a more general way at the end. But if that's the case, we'll directly go over to the first of the use cases, which comes from Punch for NFDI, from Dr. Elena Saki from the Leibniz Institute for Astrophysics in Potsdam, who, to my knowledge, recently also joined the supercomputing in eScience. There, she'll speak about creating data flows leveraging RIANA for reproducible analysis of dimensionality reduction workflows. Please, Elena, the screen is yours.
Yes, thank you. Hi, everybody. I'm gonna share my screen. And actually, Harry Anke will do a brief introduction at the beginning, and then I will take over. So I hope you see my slides.
Okay, thank you, Elena. I just want to give a little bit of context for the next slides and the workflow. Can you please go to the first, the next slide? So just a recap, the fundamental physics are already dealing, say, for at least 40, more than 50 years with digital data and working with considerable amounts of this digital data. So consequently, we have within the different communities, sub-communities like the high energy or the astroparticle, the astronomy and astrophysics and hadron and whatnot. So all the fundamental physics directions. We have a couple of developments which go back a long way. For instance, the first data management unit was shot into the sky with a satellite. So on board, they already had some kind of data management notion. It's nothing that new. So we have a lot of data storage formats. We have descriptions of this data, that is metadata and their schemas. We have default tools for data handling and analysis, each within the different communities, or sub-communities, if you will. Additionally to the instruments, which grow in size considerably, we have simulation and simulated data, which became a means for testing our theories, and especially where, for instance, in astrophysics we can observe, but are able to run experiments with the way the cosmos works. So we are reduced to simulations. Scale of experiment and other material research infrastructure like telescopes or instruments on these telescopes, they especially also drove a different division of labor between the scientists and the whole personnel need to construct these instruments. So, and last point in that direction is that the scale of the data collections require more than making data fair for modern research. And next slide, please. So I would also go a little bit into the, Elena, can you switch to the next slide, please?
Can you see the?
Yeah, okay. So I put down some notions to this notion of fair. We are looking, as I already told, at very different data structures. We have file systems which build in already some of the data, metadata for the data referencing. We have streaming data. We not only have POSIX data files. So mapping data structure via classical metadata concepts is not sufficient for fulfilling this kind of interoperability, even between our communities within the fundamental research. And this in itself is, to our way of thinking, not a goal in itself. It's only for making this data consistently available for digital analysis. The next point with interoperable, with reusable. Oh, I think we skipped one, sorry, but nonetheless, can you go back, please, Elena? One slide. Okay, findability. Sorry to have skipped it. We do have working approaches managing and working with the data within our communities, but that are partially silos. We don't have working implementations for access of the data by other communities. But we, for instance, have registries for data publication sites in astronomy, especially we have with the Virtual Observatory, of course, already common protocols, also using OAI PMH, and also other protocols which are catering to the special way astronomer like their data, like the table access protocol and whatnot. So the findability is kind of already, in a way, in hand. We, of course, need to work, but that's not because it's not findable, but because next point it's accessible. The accessibility is a problem because we have within the communities the data sharing well developed. We have this notion of the WLCG grid, for instance, the World Large Hadron Collider grid. We have sharing data cross community is more or less tightly bound to the software tools available. And there is, for us in general, no huge problem with data privacy protection, but data curation processes, embargo periods, and computational resources for working with the data are serious challenges, require thinking of also well-worn community silo solutions. Bringing data and compute resources together is a hard problem for huge data sizes. So next slide. please. Interoperability, I already covered, so I go to the reusability problem. And just a tiny remark, reusability in the material world always takes to copying or rebuilding the same piece. You can't use it without breaking the function. That's the nice thing in the digital world. You can do a lot of copies without breaking the original or the other construction already using for digital data. But an important distinction to be made. So we have many elements of the data digital analysis which need to be consistent and stable. That is data, software, computing environment, workflows. And reusability implies in a way also reproducibility, which is a problem because some of our instruments are collecting data at a rate which is impossible to be kept. 99% roughly of the data which is measured by the experiments at CERN are thrown away after a brief analysis, and only 1% kept. And we are nearing with the square kilometer array a same situation in radio astronomy. So we have this reproducibility problem, especially to address, because sometimes we have to make decisions on the fly. And this is a huge problem where Punch spends a whole task area on making inroads there. Okay, the good news is with modern cloud environment and tools, we are able to address all these challenges. And in that sense, I will pass over to Elena to go for the use case we want to present.
Yes, thanks for the introduction. And I think this also sort of summarizes what you mentioned about Punch for NFDI tasks. And I think, yeah, exactly in this context of reproducible analysis and workflows, we probably all experience the sort of challenge of working on our analysis, our data, making our own scripts. So having something very local, probably on our laptops, but sometimes also on shared resources, but that, you know, a few years or sometimes even some months later, we are stuck because we are not able to reproduce this anymore. Sometimes the scripts are broken, sometimes even just the libraries will be updated, and also at each stage we need to edit a lot of files, and this makes it harder also for collaborating with colleagues and different groups. And in research in particular, we have this also, you know, short contracts. So, you know, when someone else takes over, it's always takes a lot of time to rebuild the infrastructure to make an analysis work. So the idea is to go from this local mindset to something really reproducible that will last for years. And even if, you know, libraries get updated, if people change, we are able to still work on those analyses that we, you know, take a lot of time to build. And of course, this involves many steps. A big part, for example, is using Git for both version controlling and collaboration, and try to edit as few files as we can, and work in this like continuous integration flow. And exactly for this reason, we want to present you this platform called Rihanna. Maybe some of you already heard about it. So this stands for Reproducible Research Data Analysis Platform, and is a workflow engine that was originally developed at CERN. and that now within Punch we are still keep developing, and now we implemented a version at AAP that is available for the whole Punch collaboration. And basically, Rihanna, as I mentioned, is a workflow engine that is sort of a complex infrastructure between client and server. There's a lot of layers behind, and also a lot of security layers. But what's interesting, I think, in this context is that this workflow engine takes care of all these steps. So from authentication, from verification of our analysis, and then executing our analysis in a very broad way, meaning both the scripts we write, but also freezing the environment and the libraries that we need to use, and also managing data's input and output. This means that we have this sort of box, which is our workflow, and inside this box we have everything we need to make this run. So it means that in 10 years we go back to the same box, and even though the libraries will be different by that time, we will be still able to reproduce this analysis and run our code. And just super briefly, then we go to the example. This is sort of a picture trying to encapsulate the integration of this platform within the already existing Punch infrastructure. So basically it's at the center of many different steps, including storage for Punch, compute for Punch, and then this whole security layer, so this AI requests, and this is now fully integrated, managing both the workflow, the databases requests, and saving the results. And if you have questions about this, we can also expand on this later. But now, yeah, let's go into the practice. So we wanted to present an example. In this case, it's like a dimensionality reduction algorithm that we wrote in Python. This is, of course, just an example, but you can manage any kind of code and any kind of analysis that you already have. Just with a few steps, you can update it to make it work on Rihanna. So super quickly, just for context, but it's not that important, we wrote this script comparing 3 different algorithms for dimensionality reduction, UMAP, PCA, and TSNE. But what we really wanted to show is sort of the data flow we use in this workflow. So we are going to have some data coming from a TAP service. There will be an analysis part, and then there will be both upload and download from S3. And then downloading of the final results. So S3, if you don't know, it's like Amazon-based storage service that we have at the AAP, and it's very useful and convenient to manage like this big data. You can divide it in chunks, and it's also very simple to access it. So this is just a scheme of this workflow. We have 2 main Python scripts. The first one actually performs the dimensionality reduction. So it will ask for some data from a TAP service, in this case, the Gaia archive. Like Gaia is a very, very nice mission that we are also hosting like the archive at the AAP. And then this will just push back the results to this S3 storage. And then the second script would grab these results and just combine the plots. So it's quite simple example conceptually, but it deals with these different data services. And as mentioned, like we have this workflow engine, which is Rihanna, that is also taking care of security, not only for authentication, but also because S3 requires some keys to be accessed, and we can very conveniently store these keys as Rihanna secrets. So before going to the workflow, we save this as basically couple of very simple commands so that later we can access these keys as simple environment variables, which is very, very convenient. And how Rihanna works is basically we write a YAML file. So one simple YAML file that will organize the workflow. So taking care of the input, output, and the parameters and the computational steps we need. And then we can specify also the compute infrastructure that we want to use. And we have some memory to just make it run. So just to show you an example of this YAML file, first part is going to take care of the input files. So in this case, the files will be the 2 scripts that we have in Python. And then we can specify some parameters like, my user folder on S3 and the number of iterations I want to make. And in this case, the data are all remote. So the tap query will happen inside the Python scripts. And then after, everything runs, we write a part which is going to take care of the output files. So in this case, I will create a folder results. We'll define a PDF for the merge plots of all these 5 iterations. And again, in Rihanna, we can just then give a command to download these results on our local machine, for example. And then the workflow itself is written as follows. So we can specify different types. The simplest one is this serial type, and then we have different parallel, like for example, if you know them, CWL or snake make. And then we're going to have in the specification part 2 steps. The first one that is actually running the dimensionality reduction and uploading the results on S3. And the second part is going to do this plot combination. And something that's really important, and it's a mandatory keyword in the Rihanna YAML file, is this environment. This can be a super simple environment, for example, a Jupyter-based one. But for this example, we also created a customized image that you can see here. And this is also super important because it's the key of reproducibility. So in the future, we're going to have the same environment to run this analysis. And if we don't delete the image, this is going to work. And actually, by the way, both this example and the images we created are on our Punch GitLab and are publicly accessible if you are interested. And again, this is like the second part, combining the plots and grabbing and the files and re-pushing them to S3. And just to give you a look of the platform, how this works. So the homepage will be like this, and now we have this Keycloak sign-in that's taking care of this AI authentication. And once you're in, you're going to see here a list of all your workflows. And the workflows can be run either from the terminal. So again, quite simple commands. For example, to run a workflow, you just do Rihanna client run, and then the name. And then at the end, you can download the results with Rihanna client download results. Or you can also, for example, what we did in GitLab for our tutorials, you can create a button that will directly go to the platform here, and then you can sign in and again see the list of all your workflows, and this will start automatically. And once you're in, so again, this is your sort of homepage after authentication. You can just click on one of the workflows, and you're gonna end up in this other screen where you have 4 tabs. So in the first one, you're just gonna see the logs. And then the engine logs. Then the next tab, you're gonna see actually the job logs. So in this case, you can see, okay, we created a random scene, we did the 3 projections, and we upload the plot to S3. And this for the 5 iteration that we set. And then completed. Of course, if you have any errors, you might have in both tabs some other logs with some warnings or errors. And also this is very nice because on top you see the steps. So if you remember in the YAML file, you specified the steps, and you can select here and see the specific logs for each step. You can see the time you had to the analysis took to run. You can see the backend, and in this case is our Kubernetes infrastructure. You see the image that you use, so the environment, and then you see the actual command that was run with, for example, here the customized parameters that you chose. And finally, this workspace tab will just give you a list of all the files you uploaded and then the files that were created. So in this case, the results. Something also really nice is that you can click on these 3 dots and open a Jupyter notebook. So you have this either Jupyter notebook or now we upgraded to a Jupyter Lab view. And you can actively work on those scripts and files, and then you can also open a terminal and do basically whatever you would do on a Jupyter Lab. And also you can do the same from command line, then specify also a different image, for example, if you need it. And super quickly, there are some developments going on, as I mentioned at the beginning, and really recently. So last Monday and Tuesday, with a part of the team, we were in Bonn, working, like we organized this hackathon together with Bonn University and KIT colleagues. We had very specific goals. So in particular, we wanted to integrate this Rihanna with the existing Compute for Punch and Storage for Punch. You can see here our GitLab dashboard and a lot of like completed items. So it was a very successful 2 days. We were working on a pre-production instance that we prepared the AP, running a development version of Rihanna, of course integrating with the existing key clock authentication, and then integration with Compute for Punch. So now we have the HT Condor interface that was already used at KIT, and you can specify the backend when you run the analysis, and you can use different resources, and also with storage for Punch. So not only like using TAP or S3 or local like Kubernetes storage, but the integration with storage for Punch. And we're still working quite closely with the development team at CERN to add new features, because this is also like in development for them, and to just keep improving. And for example, just here is a test we run, and you can see the difference. Like for example, here you see the backend is now Compute for Punch. And just to end, this is just a picture of us at dinner, happy with what we achieved. So thanks a lot, and if you have any questions, please ask.
Yes. Thank you, Elena, for this very interesting and fascinating talk. And yeah, as you already said, we are open for questions now. I don't see any questions in the F&A or Q&A yet. If you have questions, please raise your hand. Otherwise, maybe I have one small question. Since Rihanna is already around for a few years, do you know how broadly in use it is in the community already?
So I think since it started at CERN for the particle physicists community, it's quite used. We are also introducing it at our institute, and of course within Punch. And like many people were very interested, we also ran a tutorial at the beginning of February, and some people are here, for example, are testing it. And becoming more and more interesting. Just this morning I received also questions about it by other colleagues, and Harry, maybe you want to add something?
So
yes, if I may.
Of course.
So currently we are running Rihanna on the Punch resources, and they are basically restricted to Punch members and collaborators. We are planning to open up that, but on the other hand, we have to look at the limited resources we have. So we open it up for tutorials, and already in the first tutorial we gave in February, there were, for instance, from Rhesus and from biomedicine, there were some included. So the problem we have is we open up with Rihanna pathways to navigate the whole resource landscape. On the other hand, and it's included in the Punch AI, so this Keycloak instance at AIP just redirects queries from the services to the Punch AI, and in that sense, we already implemented a lot what other communities also are working on, that is getting a kind of single sign-on for that NFDI. But going back to that, we could probably talk about including other resources, but we can't just serve with Rihanna without agreement from resource providers to distribute workloads to them. Compute resources are precious, S3 and other storage resources, they don't come for free. So that's the let's say the silent problem we are working on. On the other hand, you have to consider that as what it is. It's a way to navigate the very complex resource landscape we have. So we need agreements from resource providers, and obviously we also need to find ways to deal with data you plainly can't transport for each and every analysis back and forth across the network. I don't know how many of you already tried to let's say, access via the network, downloaded a couple of terabytes. You sit on end on that. So our concept in that case is also to try to bring the data and the compute resources together. That's a task of Compute for Punch. So there is a lot of additional fine-tuning work required to open it up more. But we are open to talks about that. Our goal is to make this really powerful engine also either deployable for other communities with their resources, or find a way to include resources which can be used by other communities. And then we can also provide Rihanna services for that. But as I said, there is a lot of technicality still involved we didn't address here. For instance, to create containers which are customized to your task, you need a GitLab, and a GitLab continuous integration working in the registry where these containers then can be accessed and whatnot. So I don't want to go into the nitty-gritty details, but that's where we are. And we, of course, are happy to talk to other communities if they are interested in deploying this. And on the other hand, we are closely working with the developers from CERN to make to include all the Punch developments also in the general release of Rihanna software.
Okay, thank you. Yeah, I think that's a common challenge everywhere, that we're still facing resource limitations. And I also see from Christian Schneider remarks that Rihanna is currently not, to their knowledge, not used outside of CERN. So the comparison with NFDI, with Punch for NFDI is, of course, also interesting from this view. Okay, I think for now I don't see any other questions. If that is not the case, I would like to hand over now, thanks again, of course, Elena and Harry for the presentation, and hand over now to Dr. Saras Menon from Mathwerk for the next presentation. He's from the Max-Planck-Institut für Eisenforschung from Düsseldorf. And he'll speak about creating and running automated workflows for material sciences, science simulations. So please, Sarah, the screen is yours.
Thank you. I will get started with sharing the screen. I hope you can see it now. Yeah. Perfect. Thank you so much for the introduction. So my name is Sharat Menon. I'm from the Max Planck Institute for Sustainable Materials. It sounds different to just the introduction that was made. It's just that we got renamed a couple of days ago. So we are now Institute for Sustainable Materials, not Iron Research anymore. But yeah, we do similar work anyway. Yes, so today I'm representing NFDI Mathwork, and I would like to talk to you about creating and running automated workflows, especially with the focus on material science applications. So let's get started. Yeah, so there was a nice introduction already about FAIR data in general, and the previous talk by Dr. Elena also covered a lot of aspects that I wanted to cover today. So we are tackling similar problems here, which is how do we go from FAIR data to FAIR workflows, which are reproducible and so on. So what are workflows? What are computational workflows? Let's get started with that. So they're often complex multi-step methods which are linked together to produce a data output. Yeah, they can be used for data collection, preparation, analytics, predictive modeling, and also simulations, which is what my background is. So we already saw some examples now. So one can think of computational workflows in general as enablers of automated data processing. So even if you're an experimentalist or from the computational side, you're probably using some workflows in your everyday life, right? So to get some data, post-process it, to generate data, whatever be it. So when we imagine now how FAIR would translate to workflows, it's not just enough to stay on the data side. So data is an important aspect, of course, because FAIR workflows and data are interlinked with each other. On the one hand, you need data as an input for these workflows. And on the other hand, we can actually tackle the problem at the level of workflows and make sure that the data produced is fair, which would help the user a lot. The next aspect that one would have to consider is also fair software, because a workflow itself is a piece of software, and it can include multiple smaller pieces of software which are linked together. And finally, this brings in some unique requirements, right? So these unique requirements are mostly on the R side, which means they can be related to the reuse, rerun, replicate, repurpose, recycle, and what I will focus on this talk, reproduce. So these are all important aspects that we have to consider in this, because the added complexity for workflows is that you have to execute it with a given computational environment, dependency, software tools, and so on, to make sure that you get the same data at the end of the day. Great. So with that, I would like to give a small example of why this is not important and why we really need to focus on why this is important and why we really need to focus on the reproducibility aspects. So this is a paper in NPJ Computational Materials, which has been cited quite a number of times. So what they try to do there, it's a machine learning work in which they predict the band gap of inorganic materials with a machine learning model. So you can see on the graph on the right, the original predictions, which are in red. And a couple of people tried to reproduce this and run it again. And to their surprise, what they found was that the results could be anywhere along these blue plots, right? So that we're talking about band gap differences of like more than 2 electron volt. And this depended a lot on what random seed was used for the whole workflow. So obviously, this is not something we want, right? So this is something that we have to avoid. And that is the aim in principle, and one of the aims of reaching fair workflows. So in the paper, they also summarized the major challenges that they had to go through in reproducing these results. And they were: one, sequential code organization. So in principle, which steps were executed in what order? So which parts have to be tackled properly first and then on, and so on. And reporting computational dependencies and versioning. So which versions of software were exactly used for this purpose? And how the workflows itself then can be version controlled. So our solution towards this and to handle fair workflows is known as Spyron in Mathwork. So this is a tool. It is a workflow manager that we use. And it's mostly built on 4 pillars, very similar to the talk we saw before. So one is ease of use, right? So how do we separate user and code space, and how can we automate things in a way that the user itself doesn't have to be bothered about? certain code-specific nitty-gritties. How can you scale these things? How can you make sure that something that runs on your laptop can then be submitted on a high-performance computing cluster and it works there? And also, very important is how you can share these workflows that you make and how you can extend them, right? So I thought today that we can do this with a live demonstration. So we also go about it with a more programmatic approach. So if you want to follow along the tutorial, which I will switch to, you can put this link in your browser. It is lmy.aa/workflow. And it takes a moment to get started, but then you will be faced with a Jupyter Lab interface, which then you can use to execute them. So meanwhile, I can introduce what actually we will do. So we have chosen a simple enough problem, which is to calculate the Young's modulus of a material from experimental data. So whatever be your background, you should more or less be familiar with Young's modulus. So it's just the response of a material to a stress and how it behaves. And it is a general enough example in the sense that it uses some data and calculates a material property out of it. For the data, we have tensile test, which I'm sure a lot of you are familiar with. But what happens there is that you have a sample of a material, and then you elongate it. And while it's being elongated, the force and the elongation are measured and saved somewhere. So in this case, it's in a CSV file, which comes from a machine. And that can be used then to transform it into a stress and strain, which looks something like this. As you strain a material, it undergoes a stress. And from that, you can calculate the Young's modulus, which is just the slope of this line, which is in the linear part. So that's the example we will try. So with that, I will quickly switch my screen now to our Jupyter Lab instance. So if you were able to start it up, it should look something like this. So this example was also used for the DPG spring meeting, where we also presented this example. And the data itself for the tensile test comes from BAM through the project digitalization project Material Digital, which is also very closely related to NFDI network. So as I showed before, so this is the problem that we will tackle. So let's get into it and see how we actually do this, right? Of course, if you're not familiar with the Jupyter Lab interface, there's a bit of crash course on how you can run this. I will not go too much into detail in this for saving time. But the main command, if you want to execute it together with me, that you have to know is just Shift-Enter. So if you click on a particular cell like this and press Shift-Enter, you will see that there is a star and the number appears there, which means that the cell is executed. For those of you who are familiar with it, sorry for over-explaining these things. But yeah, so the first step then, as we saw in this picture here, is that we have to read in this data, so from the experimental side. Yeah, so how do we do this? So as I mentioned before, we take a little bit of a more programmatic approach to workflows and how you can use them. And for that, so the first function that I show here is called read input. So what this function does in principle is that it takes a file name, and of course you can also click on this folder icon here, and then it shows you what folders and files that I have inside here, right? So this is the data that we have there, which is my data set, which is a CSV file. And the first function just takes this in, right? And takes in addition an area, which is the cross-sectional area of the sample that we saw before. And what it does is that it does some unit conversions in there, and it then reads the CSV file, calculates the load to the stress, and calculates the strain, and gives the output as a stress and strain. So yeah, so it reads the raw files, processes some conversions, does some unit conversions, and gives you the stress and strain as the output. Yeah. And now you will see that on top of this function, we have added something extra. So this is what we do with Pyron Workflow, which is our template, which is our module for creating computational workflows, right? So this is the only thing that you need to add on top of the code that you have lying around, right? So whatever script or tools that you use to run these calculations and things, just need to add these things on top, right? So what it does is that it creates it into a Pyron executable unit, which you will see in a moment. So let's execute this once again. So that runs very quickly. And once you have this, the next step is to use the stress and strain to calculate the Young's modulus. So as I showed before. Once again, there are some unit conversions and so on, but what in principle it does is that it's just simply does performs a linear fit and then calculates the Young's modulus as a result of this linear fit and returns the value, right? So that's what the function does. Now, a crucial thing here is what I have called the strain cutoff. So as we saw before, you have to choose the elastic region, so the straight line part of this curve, and you can choose what cutoff you use, right? So this is a variable parameter that you can choose, and depending on it, your results will change. So why is this important here? Because we have chosen a particular value, and the calculated Young's modulus will depend on it. At the same time, this gives us a good example of our everyday scientific tasks that we have to handle, right? So often we have the same thing. We have to vary certain parameters and see how our results are converged or not. So it's a good example of these sort of tasks that we might have. So let's execute this too. And the final step is just to plot these results. Yeah, so I just want to plot the stress and strain to make sure that it looks reasonable and it is something that we know. Okay, let's execute that. So we have our 3 different functions, and now the thing is to put them together in a workflow. So as I mentioned before, it's crucial that we know which steps were executed in which order, and that ensures that we get the same results at the end of the day. In this case, we can then start doing this by creating a workflow object. I just call it Young's modulus. This in principle can be any name. And I say that, okay, I have a strain cutoff value. I have a read input step, which then calls our read input function. I have a Young's modulus step, which calls our calculate Young's modulus function that we saw before. But now this is where the interesting things happen, right? So this takes 2 input values, which are stress and strain. And you can see that I specified it like this, which says that from my workflow, take the read input function, which I defined before, go to the outputs and take stress. Yeah. So it tells our workflow that actually the inputs for this step comes from the previous one. So that's how you link them together. And finally, we have the plot function. So once again, it takes the outputs from the read input one and plots it. Yeah, right. So we can also execute that. And finally, how do we actually run the workflow? So now we have composed it, and now we just need to execute it with the given data set in there to get an output result. So we can execute it by providing these input names. Once again, the file name, cross-sectional area, and I just do this. And you can see that it runs and creates an output of how our stress and strain looks like. So that's all fine, it works. It also has some neat functions. For example, what is the draw function? So what do we see here? So this gives you a layout of how your workflow was executed, right? So it starts from the input. You can see that there are different input functions, such as the strain cutoff, the in file name area, and so on, and how they were passed on to different parts, right? So there was the read input function, which took the file name, and it gave its outputs to the Young's modulus function and plot. So you can already see that these 2 functions were not sequentially connected to each other. So they got the input from the same one before, and they could be run at the same time. And the final outputs are shown. So this is a good overview on how the workflow looks like. Of course, it can get quickly very complicated depending on how many tasks that you want to run, but still it can be used for some quick debugging and understanding what happens when you run the workflow. Now the question is, this is well and nice, and this is a workflow that runs. Now, how do I give it to my colleagues who are working on some other tasks, but want to use this particular aspect? Let's say they want to use the Young's modulus and run a continuum model on it, an FEM, finite element method model on top of it. So we want to pass it to them. And that's where what we call as macros come in. So a macro is just a reusable instance. So once we have composed the workflow, you can share it as a macro. And the macro gives 3 main benefits, right? So one is reusability. So you can simply take it and use it together now with different input parameters. It's composable. So now you can take this workflow and build things on top of it. So it's like a unit of a workflow. And finally, you can share it, right? So other people can use it. So the macro now looks very much the same as we did before. So instead of the workflow, we can define a function which has the input steps. Once again, read input, Young's modulus, and it returns the output parameters. yeah, and you use a different decorator and give it some names. And I can create my macro like this, right? So modulus is my macro, and then you can run it. And then you can simply execute it with different values of input parameters. Yeah, so if you wanted to say, let's use a different value of strain cutoff, I can simply use it, and then you see that I get the same results out of it. Good. Now I already come to the last few parts of my talk here, is that now we have seen how you can compose a workflow, make it into a unit that can be exchanged and used by other people. And the question is now, how do I scale it up? Yeah, so now it's mostly not just one parameter, right? Maybe I want to run it over thousands of different parameters and see which results make sense, what are the outputs, and so on, and how they can be compared. And for that, we have what we call as a project. So in Python, a project is a central object. So you can think of it as a project in terms of what we do. Yeah, so I want to do some stress strain calculations. So I call it a project, and we can create it like this. Now some interesting things happen, right? So if we go to the file browser there, so you can see that a folder was also created for you. So what the project does is that it manages your folders, the calculations, in a way that they are all independent and they're all saved and they're all reproducible. So from the macro that I created, yeah, I can just make it as an input. Yeah, I pass it on to a Python, Python object, what we call as job. So this can be done in this way. And now you can simply call the run function. So the job.run function once again does the same thing and provides you the output, right? So job.output Young's modulus. Now you can see that we get the same result out. So now you can see how we do it. I want to, let's say, go over all values of strain cutoff from 0.03, up to 0.3, and like take 30 values out of it, see what results I get. So you can simply put it inside a for loop. Yeah. So and I create different jobs for each of these tasks. Node job, I call it. Once again, pass my macro to it. And you can see now the strain cutoff is just a parameter that you pass to this whole unit. Yeah. And I can call run. And you see here that they start executing. And it gives you a message that these jobs were run and saved. If you were submitting this to a high performance cluster, instead of executing at this time, we would submit the jobs and monitor them and see that they are executed. And if we go back to our project now, you can see there are a whole different number of files that were created, which stores the output of your calculations. Good. So with that, we can quickly take a look at how we analyze it. So we are at the final task. Yeah, we managed to compose workflows, run them for different values and get all the results. So now how do I bring them together and take a look at it? So with that, for that, we have what we call a job table in Python, which is like a bird's eye view, a glimpse of all the jobs that were run, yeah, with a lot of different information stored in it. So you can see that there were the status of the jobs. Let's go to the top quickly. There was the IDs of the job status, and for example, the timestamps of when they ran and what tools they used and so on. Yeah. So we can use this table, accumulate more information into it, and use it for the further analysis to arrive at these results, right? So I can create a table, as you saw here before. So once again, like I mentioned, now we have to select what information we want on the table, right? So for me, that would be the Young's modulus that I calculated, yeah, and the strain cutoff. So that's the two parameters that we want to compare and see how it looks like. Oh, okay. So another thing I did not mention, so you can also access these results in a user-friendly way, right? Storage output, and all the outputs are listed here. So I create just two functions that goes into my individual job, takes these output values, yeah, can execute them. And then I can add it to my table. Yeah. So how do I add it? I just call a table.add function and Young's modulus, which corresponds to this Young's modulus function here. Strain cutoff, which corresponds to this strain cutoff function here. And as always, I call the run function, gives you a couple of different bars, and that worked. And I can extract the final results by using this get data frame function. So let's run it. And I end up with my final result here, which again has the job IDs, the Young's modulus for each of them, and the corresponding cutoff that was used for the calculation, right? So we can plot them quickly. So each of these points is a single calculation that we performed. And on the y-axis, on the x-axis, we have the strain cutoff and the corresponding Young's modulus. And the dotted lines were the experimental values that we had. So you can see that how if we chose it too low, we didn't get right results. If we got it too high, we are including the plastic region into the calculation, and therefore we also don't get good results. And it worked for a particular region, which is the right choice. So it sort of illustrates everyday problems that we might have in our field and how we can tackle them in a way that is fully reproducible. And you can do this and is shareable. Hopefully, a lot of you were able to run this yourself and get same results, right? Yeah, so that's pretty much what I wanted to show today. So we didn't really do any simulations, although I told it would be about simulations, but we can do it. There are some links out here. We also covered a lot of topics today in a very short interval of time. But since you have these notebooks and binders, you can probably run them on your own and try around a few things. They will be active for more time. You can use it. Of course, my email ID is also here. It's just s.menon@mpi.aa. So if you have any questions and so on, of course, feel free to reach out. So with that, I'm at the end of my presentation for today. If you have any questions, I'll be happy to answer them. Thank you so much.
Thank you, Zaras, for this great, interesting, and descriptive presentation. And already I saw a raised hand for a moment. Now I see a raised hand again from Harry Enke. Please go ahead.
Yeah, thanks for this very instructive use of the Jupyter Notebook environment. What I want to know is, this is something you run on a central instance of a Jupyter server, or is this something you can run on any notebook?
Yeah, that's a very good question. You can run it on any notebook. That's the short answer. So for the demonstration purposes, we use a MyBinder instance, which is just a throwaway instance of Jupyter Lab that you can start on your cluster, on central resources. How we achieve this is through a Conda environment. So we try to fix all the software dependency that we use as a Conda environment, which is then converted to a Docker image in an automated way, and it's hosted for use. So, but all of these packages are installable and we have tutorials to do it. So you can use it in whichever machine that you want to do.
Okay, so the salient point for reproducibility is you create a Docker image with this environment where you can calculate the Young coefficients.
Yeah,
okay,
correct.
Thanks.
Thank you. Are there any more questions? I think I saw a raised hand before. Another one, but I don't see it anymore. So if you still have the question, please raise your hand again. And just let me quickly check also the F&A. I don't see anything there. Yeah, maybe Sarah, you were already too descriptive and clear in the beginning.
But of course, if there are further questions, just reach out and try it around and so on. Yeah.
Great. Yeah, now we have the opportunity. Okay, in that case, I would like to hand over to the last, but of course not least, presentation from Dr. Oliver Knodel, and I hope that my information is correct this time. He is group leader for data management in high performance computing at the Helmholtz-Zentrum Dresden-Rossendorf. And today his presentation will be about overarching data management ecosystem Heliport. Please, Oliver, the stage or screen is yours.
Okay, so thank you for the introduction. And yes, today, last talk for today. And now I'm really not on the workflow level as in the talks before. I'm more one step higher on the facility level. We also embed workflows, but we start completely on a higher level. So my talk is on our overarching data management ecosystem called Heliport. So let's introduce a little bit our infrastructure and also our facility. In the photon and neutron science, we have so often larger facilities. For instance, here, a smaller center is the Helmholtz Center at Dresden-Rossendorf. We have at the end only 1,500 employees and in the end, 700 scientists, member of the Helmholtz Association. And our challenge is that we support in the end 3 different research fields. So energy, health, and matter. Matter especially important for our Daphne for NFDI project. We have large facilities. For instance, here our Elbe Center for High Radiation Power Sources, many large experiments, different beam times. And here our challenge is that we have so often scientists not really coming from our center, we have visiting scientists. And for us, it is important to bring all these persons in an easy way to our infrastructures and also the services involved. And there we are at the level of data management. So this is really a big topic for us. We have also a highly magnetic field laboratory, so different experiments, sometimes the same infrastructure, but sometimes also special resources, systems, services in use. And we have an ion beam center. That is our landscape from the experiments at HZTR. And in the end, we as a group for data management, we want to bring everything in our end-to-end digital data lifecycle. So we support many steps of our different research experiments with specific tools. So with electronic lab books, interactive analysis, publication of data sets, so publication systems, repositories. We have also scientific workflow management systems and tools, also an HPC cluster, but often our visiting scientists, they don't know that. And typically we want to support really everything. So on our research life cycle here on the right side, typically it starts with a proposal coming in our center. Then in theory, we create a data management plan, collect the data, analyze the data. So there we are at the level of the workflow, of the analysis workflows and so on. Then after data generation and derived data sets, we have to archive everything and store the data on our data storage system in our center. So that is written down in our data policy, so that is necessary. And we have also systems to publish in the end selected data sets. They can be reused and so on. So our complete chain of tools is there in this nice circle. But a uniform and smooth access between all these services is really hard work. And we need also documentation. We know that. Another big construction sites. So when we go down to our real infrastructure we have at HZTR, we have for all these different steps, somewhere a system in our ecosystem. So we have here, for instance, a proposal management system. We have time series databases, we have the documentation, workflow somewhere, publication in the end. And when the data is published or the software is published in our systems, it is also findable using D2Find. But this infrastructure is complex. Not only complex for visiting scientists, also too complex for our scientists at HZTR. So we need here documentation that can work, but we tried it. That's not the best way to go. We need something different. So we tried to build a system where every system, or we try to build a web page where every system which is involved in a specific experiment is available, is listed, is accessible to every member of the project. First, we named the system Data Management Guidance System. That was maybe not the best title. So we submitted in Helmholtz Metadata Collaboration Project. There was an acronym necessary, and now the name of the system is Heliport for Helmholtz Scientific Project Workflow Platform. So a system where really everything is accessible. And the picture of a helicopter flying high above a real experiment, and on the ground you can see from the high that different systems are involved and also which systems are involved. So that was the idea. And in theory, in the future, we can also provide all this metadata on these different subsystems involved in the experiment to a knowledge graph. And then we can hardly combine really everything. So the idea for our HMC project Heliport was a common entry point for experiments at HZTR, at Research Center Jülich, at GSI, hopefully in the future, and so on. And everything what we want to provide is a web interface where we can dynamically integrate different subsystems which are available somewhere, and also the data sets and workflows used and created during the experiment. And this is the system in the end. It is a starting point. When you log in, you can select a specific experiment, and every experiment described in Heliport has such a landing page. Under systems, we see, for instance, here that there is a version control linked, so where the source code is. We see where the data management plan is, where the documentation is. We see the real data sets on our archives, on our file systems. When they are linked here in Heliport, we can see also jobs executed on our cluster, HPC cluster, and we can see in the end the real scientific publication and also the data publication and so on. Project members of our HMC-founded Heliport project were at the beginning Helmholtz-Institut Jena and Research Center Jülich. And the idea was in the end to create a more fair and comprehensible project description. And this includes in the end such workflows as we have shown in the as we have seen in the talks before. We can export all this information on the different subsystems to metadata scheme. We can also provide crosswalks to schema.org research projects, so it is reusable and also interoperable. In the end, the motivation to use Heliport, now this was the facility idea behind everything. Now we switch over to the user perspective. How can we help our scientists? And typical questions from our scientists are, how can we automate recurring processes and keep track of status and data products? So when a project member has a nice workflow, we should provide the information that there is a workflow and where it was executed. And we should also show where the real data sets are stored in the end, so that not every scientist has to rerun the things which are 1 hour ago by another colleague. Also, the question is, how can we bring new team members or external scientists into our project lifecycle? So Heliport is a simple system. You can log in via different accounts, and then we can add a specific person to a specific Heliport project, and every resource is visible. Not completely accessible. We are still working on that, but in theory, that is also possible, hopefully in the future. But we think that takes a few more years. Data and the software to everything is also possible via Heliport. And we can also give a few hints in Heliport when there is data located on our file systems. We can maybe say in the future, why not publish this data set generated by your simulation to our data publication system called Rodave? Or that is also possible with Heliport. So we can work here a little bit on this level to give hints, give suggestions to build a more comprehensible and fair research experiment for our and also visiting scientists. And also the question, are there collaborative third-party services that we can use during the experiment? Typically in Helmholtz, the answer is yes, of course. There are services called HEFIS, from the HEFIS collaboration. So we can also integrate such services in our Heliport dropdown for the different steps of the experiment. So we can advertise specific systems which are hopefully usable for a specific step in the experiment, yes. And for the IT, the main question is typically what are the necessary steps towards a full comprehensible and fair research experiment? And that was the reason why we designed Heliport in the end. And we can keep track of everything which is running on our infrastructure, on our HPC clusters. So in the future, we hope that we can also reduce energy, because every project member can see that there was a workflow, it was executed, and also where the results are. Maybe. So the time scale of our Heliport project is only at the moment more or less 3 years. So we started in 2021 and now we have a nice product, but we are not at the end. We know that. So we are still developing the system, and we hope that other institutes also joining us in developing this nice ecosystem. And then we have hopefully in the future a really nice system where we can access resources on different facilities in a fluent way. So our heliport project is now over. Since last years, we started with our proposal management system to integrate all this metadata from the proposals. Then we played a little bit around with APIs. We created the overall project plan where we can add all the different systems on top level. Then our heliport project officially starts in July 2021. Then we integrated over a year different apps and features. Now we have a nice heliport website where also the heliport prototype at HTTR is available. We had a community workshop where also new project members from GFZ and Potsdam and GSI joined us. And at the moment, we have one prototype at HTTR. We connected our heliport instance to the Helmholtz ID. So everybody with an academic account can log into our heliport instance, but it is our heliport instance. So only we can create projects, but then we can add a person afterwards to join us. So we built a community website. At the beginning, there was a demo version and the HTTR version only for internal use, but a demo is not really useful because heliport provides access to different systems inside HTTR. So a demo without access to the subsystems is not really useful. So we skipped that, and our version is now open accessible via Helmholtz ID. And we have on our website also different kinds of documentations. So we have a documentation how we can use it to deploy it on an own instance, and also on talks like this one. So you can find different interesting things there. Our heliport features are, it's in the end a long list, but I think here it is better to just look at a small demo system here to see a little bit how heliport can support real research projects. So here I choose our TLB experiment because the experiment has a nice data flow. It is an experiment here at our center, and sorry, I was too fast. And typically we have a data acquisition system based on LabVIEW, then automated logging of the different parameters and additional manual entries on our lab documentation system, our eLab book. We have a data storage where LabVIEW stores in the end the data from where somehow a data analysis is started. And in the end, we need a data publication. So that is the flow of the experiment. And our idea was, okay, we can set heliport on top of everything, cross-link all the resources, and then hopefully also create a better workflow engine and show what happens in this experiment to every visiting scientist. At the moment, LabVIEW is completely internal, but the workflow is then started on our HPC cluster, and no one of the visiting scientists even knows that there is a workflow. And our idea was to provide all this information and insights via heliport. So I introduced all the subsystems, and for this TLB experiment, we mapped different resources. Well, we used different resources here. We used the proposal management system here on the left side, and our detector is in the end our LabVIEW instance. We use the electronic lab book and so on. And workflow engine, our workflow itself is stored on Workflow Hub, so it is findable, accessible, and hopefully also reusable. For the workflow itself, we used in the end our HPC cluster, and finally the publication systems. So first there is a proposal. There is a scientist from somewhere outside HTTR. The proposer, the principal investigator, can apply for beam time at our center. At that point, the principal investigator has to submit also the experimental team, the idea, the title, and so on, all important information. After that, the person can register the complete team to Heliport or in Heliport, and then all the persons can access the resources here in our HPC infrastructure. And that is the important thing, because at the moment, when everything works really very, very good, only the principal investigator has an HDR account and can access everything. But now, with Heliport, the complete team can access most of the resources. In many cases, only read access, but we are still working on also providing write access to different subsystems. And in the end, we have the scientific publication, and there it is important to say, we have typically the metadata of every person coming to the experiment or involved in the experiment. In the end, maybe 40 names, and we have the data publication system, and then we have to copy and paste all the different names from the PDF file to the final data publication. That is really hard work. It takes sometimes up to 40, 50 minutes. With Heliport, we have all the metadata available. We have complete access to our proposal management system and can say the data is located on our file systems. We have all the names, title, abstract. We have everything. The publication of the data is done within minutes through Heliport as a background job. And in the end, yes, we can provide everything happened during the experiment if everybody agrees to a knowledge graph. Proposal submission looks in the end like this shown here. So we have the proposal management gate at HDR. All the information are then transferred to Heliport. Here I have all the names of the persons coming to the project. So I have access to all this metadata. Then the next step, after the beamtime application, we create in an automated way, or we can create in an automated way, the Heliport project for a specific beamtime. It looks in the end like this one here. The owner of the project can then add different systems which are used during the beamtime. For instance, here we have systems where the documentation is stored, so our lab book, which is used during the experiment, then via Heliport accessible to everybody of the experimental team. We can also link the workflows executed during the beamtime, also the source code on our GitLab instance. We cannot provide access to LabVIEW, so only a screenshot from LabVIEW, but we can add specific commands to this LabVIEW program, and then everything, every metadata provided via LabVIEW is available to Heliport and also to our MediaWiki instance, where we collect all the information, the documentation. And we can also submit then via LabVIEW a cluster job, and afterwards it is visible in our Heliport instance down to the real output on the command line. So every member of the experimental team can now see that there is a workflow and in which step we are of the workflow. So everything is visible. And in the end, we can also see when the data comes in. And the data is then available to every member of the Heliport project. Then we can also say, okay, this folder is nice, very, very good data, representative for this beamtime. Then we can say, okay, I want to publish this. I add the label publication, and together with all the information from our proposal management system, all the persons involved, the title, abstract, metadata, which is there, we can bring in an automated way to our data publication system. And this is really nice because it took me one time for a beamtime, I think 40 minutes to prepare everything. With Heliport, it is only one click. And then, yes, okay, 2 clicks, but it is easy. It's really easy to manage. And in the end, we have all this beautiful information. So we can also combine everything, every involved system, and then we can build up relations between all these digital objects, and we can visualize everything in this nice graph to show really how everything depends. And this is really a nice feature. And we can also see what happens during the full experiment. So it is completely comprehensible. And this is the end in the end. So Heliport describes and collects all metadata from all services and systems involved in a scientific experiment. At the moment only at HZDR, but hopefully in the future also at different Helmholtz centers. And such an approach is really desirable and leads us in the end to a full, fair, and comprehensible research experiment. We have landing pages for all digital objects, and a digital object in Heliport is really everything. Every subsystem, every data set, and so on. And that's it. At the moment, we are still working on a deeper integration of scientific workflows, and one member of my team is working at the moment on figuring out if maybe Rihanna is the best choice for such a workflow system. And yes, that's it. So, thank you.
Yeah, thank you, Oliver, also for this great presentation. Normally, the higher you go with your level, the more complex stuff gets. So I'm pretty amazed that such a system could be constructed in a relatively short time. But we already have one question from the chat, and I see a raised hand, but let's go with the chat first. Regarding the vocabulary used in Heliport, is that based on an existing ontology? Or was it developed?
In parts. We are still working on that. It is in the end a project supported by the Helmholtz metadata collaboration. So we have different discussions on that. At the start of the project, we thought that is easy. Everything the same for every scientific project, but no, it's not. So it's a harder topic. And there is now also a new HMC project where also GSI is involved, called Help Me. They work on a specific metadata set for laser experiments. So we know that it is important, the vocabularies and so on, but I think we will work on that in our follow-up project. First, we created this website, this ecosystem, the computer science approach, and next level is work on the metadata.
Okay, thank you. Then I see a raised hand from Harry Enke. Again, please go ahead.
Sorry, but so first question would be, this setup seems to work well within the Rossendorf Zentrum. And maybe it's extendable to some Helmholtz Zentrum anyway, for instance, by submitting a job to Unicor, which I think, or as far as I know, is a kind of remote management system for submitting compute jobs. What I was wondering is, first off, to my knowledge, not all experiments immediately result in kind of computational analysis jobs you can run on the cluster and be done with it. So the interactive component I just had for a question, is it possible to interact or take the data out and say, okay, I will look at the data at my home institution if I'm a client for you, not within the scientists within the Helmholtz Center, but you stated also you have clients. So what about the interaction component first? And the second thing is, what if the science group, which is client to you, doesn't want their data included? How do you handle that?
we can start with the second question because it is easy. Everybody can take the data at home. Yes, you can download the data via Heliport. That is now possible. That was not possible before. Then we used typically USB sticks. So you can take the data with you to your home institute, and then you have still access to the Heliport project, and then it's on your choice. You can link the results to Heliport when they are stored somewhere where the access is possible via a web address.
So this data,
or an API.
sorry, but this data wouldn't be included in your store of things that the center
No,
had worked on.
not necessarily. But you can also add maybe via SSH a different file system on your home institution, and then this is also available via Heliport. Yes, that is also possible, but maybe not really necessary for everybody.
No,
But in theory, possible.
I just was curious about this external point of view, which is, say, often something where the context is not only constituted by being a client of Helmholtz, and I know of other institutions where this interaction between client and provider of a beamline or something is way more, let's say, complicated because they come from other communities, they have different ideas about the metadata or even have their own instrumental setup for using the beamline. So this is, this is all included and can be dealt with in Heliport, which I find very interesting, by the way.
Yeah. So it's for us the first try, and we started the project. Then we had new project members. So Helmholtz Institute Jena, for instance, they have also an own Heliport instance. Now also the GFZ in Potsdam has an own Heliport instance, and now the next step in the future is to bring them back together and build something larger. I don't know what happens. So it would be nice to have a Heliport portal in the future, and then it redirects, if necessary, to the different endpoints at the centers or universities or whatever we need, and then access local internal resources via this endpoint, maybe. But we will see what happens next in the project, in the follow-up projects.
Thank you. And the idea of using Rihanna, I could recommend.
Yeah, we need it. There's something, you mentioned also Unicore. Yes, it is on my slides. We integrated Unicore in this 2-year project. It was at that time a political decision. It works, yes, but we don't really have our own Unicore instance at HZDR. So we need something new there. And I think we go for Rihanna.
Right, and it's already moving into direction of collaboration. Yeah, any more questions? I don't see anything in the chat. I think we can also open up the discussion to general questions about all the presentations from today, if you still have something in mind. I currently don't see raised hands or questions in the chat. Okay, it's also Friday afternoon, so maybe the willingness to discuss is a bit lower than generally. So the last chance for any questions, which I apparently don't see. So in that case, join me in thanking our speakers from today. It was very interesting again. In 6 months, there will be the next workshop in this format. So stay tuned for any further announcements. Also, special thanks to Melusine, who is doing the technical background magic and keeping everything alive in the meantime. And of course, thank you very much for attending and being here today. And yeah, is it already time to wish you a nice weekend? Yeah, I think it is. Have a nice weekend and
Thank you all.
see you hopefully soon in some context.
Thank you.
Thank you.
Okay, thank you.
Bye.